So we get now to combine what we know about the order of operations with what we know about how fraction arithmetic works. And these two problems both get us to do that in more or less complicated ways. But both of them have two features, well, three features in common. One of them is that they both involve fractions. So there's going to be no way for us to get around it. The other is that they involve a mixture of operations applied to those fractions. What are the operations present in this expression? Multiplication, sitting right here, and also subtraction. And because those are two different type of operations, they're on different levels of the PEMDAS hierarchy, right? That means that we need the order of operations to navigate our way through it. Similarly, in number 7, we're actually mixing three different types of operations, right? We have exponentiation, which is the top level precedence. We have multiplication going on right here. That's the level underneath it, and so that's different. And then we also have addition, which is a different level still than that one. So both of these are going to require us to plug in our order of operations knowledge in order to evaluate. So let's take them one at a time. We'll start with the one that's a little bit simpler, has a little less going on, and that's question 6. So in question 6, where do we want to start? What's the first operation we should be thinking about when evaluating the expression 3/4 minus 3/8 times half? Multiplication. Again, order of operations tells us start in the innermost set of parentheses that we can find, and within there, do exponents first, do multiplication and division only after the exponents are done, and then do addition and subtraction only after all of the multiplication and division is done. And because these operations have the same precedence, multiplication and division and addition and subtraction, we can always convert division into multiplication, and we can convert subtraction into addition to resolve any tension that might occur there. So in this case, yes, the first thing that we want is to deal with this multiplication. So the first part of this problem, we need to figure out how to multiply 3/8 times a half. So I'm just going to ignore that bit that's in front of it so that we can focus just on this product. So how do you multiply fractions? Across, straight across the numerator, straight across the denominator. So my numerator is 3 times 1. My denominator is 8 times 2. And so when I evaluate this product, I end up with 3/16. And that's the multiplication I need to do for this problem. So now I just have to finish by putting back in the other operation, which was subtraction. And now I end up with a fraction subtraction problem, 3/4 minus 3/16. So how should we subtract 3/4 minus 3/16? What's the first thing that should spring to your mind anytime you're trying to subtract fractions? Common denominator. How do you know when you need a common denominator? In what cases do we need a common denominator? When do we not? Addition and subtraction. Anytime we're adding or subtracting fractions, the denominators need to be common before we can get anywhere. Right? Multiplication and division, we don't need common denominators. Look at what we just did after all, right? These denominators, 8 and 2, were not common, but that didn't matter. When we're multiplying, no one cares about common denominators. But when we're adding and subtracting, everyone needs to care about common denominators. So before we go anywhere here, let's try and find a common denominator that will work for both a fraction whose denominator is 4 and a fraction whose denominator is 16. What are your ideas? What could we use as a common denominator for these two? So we could use 16. So before, when we talked about common denominators, we very often used a brute force, sort of a straightforward approach, where all we would do is just multiply the two denominators. And in that case, that would lead us to 64 as a common denominator. That will work. That will always work, to just multiply the two denominators. But if you can invest a little bit of time up front in thinking of finding a denominator that's smaller, that may save you a little bit more simplification down the line. But it comes at the cost now of having to think a little bit harder about how to balance these numerators. So looking at the second fraction first, 3/16. How should I change that numerator to balance its denominator? Almost a little bit of a silly question. Yeah, we didn't change the denominator at all, so we shouldn't change the numerator at all. Another way to say that is we really just multiplied the denominator by 1. And whatever you multiply by in the denominator, also needs to be multiplied in the numerator, but multiplying by 1 is an invisible operation, right? So that second fraction doesn't change, is the short part of that story. It's only the first fraction that we've had to change to get these denominators to be common. So then the question is, how? So how have we turned 4 into 16? Multiply by 4. And therefore, what do we need to do upstairs? Multiply by 4. So 3 times 4, that's going to give me, for the numerator of my first fraction, 12. Great. That right there, that was the hard part in this whole process. That's the step that's going to require the most thinking. It has the heaviest cognitive load. It's where your brain works the hardest, right? Is in thinking about what common denominator will work. And then once you've decided upon a common denominator that will work, switching the numerators out so that they match. Cool. So now that the denominators are common, how do we actually carry out the subtraction? First of all, what do we do with the denominators? Nothing. Keep them, exactly. Right? The denominators are your currency. It's the denomination on your dollar bills, right? And so if I take 12 $10 bills and I take away 3 $10 bills, what I have left is a stack of $10 bills still. The denomination doesn't change. What does change is the numeration, how many of them we have, and that's where 12 minus 3 gives us 9. And sure enough, that's the 9/16 in our answer key. So our second example, problem 7, is mixing 3 types of arithmetic. An exponent from this level of the order of operations tree, a multiplication from this level, and also an addition from this level. So that's 3 different levels, which means in our order of operations we can't really skip any steps. We got to go one at a time, top level down. So the first evaluation that I want to do is which one? The first thing I should do is worry about 1/3 the quantity squared. And so then the question is, how do you square a fraction? Yeah, same way you square anything. Multiply it by itself. This is something worth writing down on the inside of your eyelids. Backwards, or whatever the phrase is. Squaring means multiplying by itself, which is kind of an obvious thing to think about right now. But many people forget this later on down the line in the semester when we start to get variables into the mix. But this is always true. This is what it means to square something. It means multiplying by itself. So we can turn this exponent, which we can't do with every exponent, but for the exponent of 2, we certainly can get away with quite easily just writing this as 1/3 times 1/3. And these parentheses here aren't really doing us any favors, so we can just get rid of those. Go away parentheses. And now I just have a multiplication problem. What do I get when I do 1/3 times 1/3? Yeah, just multiply straight across. I'll get a 1 on top and a 9 on the bottom. And so I end up with, from this multiplication, I end up with 1/3. Or sorry, 1/9. 1/9. Okay, so far so good. That means we did our exponent and we have no exponents left to worry about. So now we can turn our attention to the multiplication that came before it. Right? 7/8 times that result. 7/8 times 1/9. And just like in our last problem, we get to answer the question, how do I multiply these two fractions? Just straight across, exactly, right. I'm going to keep asking you that until you get tired of answering it correctly, as you have been. 7/72. So at the end of that process, I've got 7/72. But now is the time to remember that that process also began with this fraction 7/9 out in the front, which is being added in. So I've kind of hidden a part of the problem selectively at every stage just to keep ourselves focused. But now this is the whole problem, right? 7/9 plus 7/72. Okay, and I'm adding two fractions. So what must I absolutely do? Find a common denominator. Perfect. So what's an example of a denominator we could use which is common for both 9 and 72, which is a common factor of both? 72. So actually, just like in our previous example, one of the denominators was itself a multiple of the other. Over here, 16 was already a multiple of 4, so we actually got to keep 16 as the common denominator. Same thing here. 72 was a multiple of 9, so we can just keep 72. And if I keep the denominator on my second term, that means I get to keep the numerator too. Right? What about that first fraction? How have we turned 9 into 72? Multiplied it by 8. Very good. 72 divided by 9. So, do the same thing to the 7. And I have to go in my mental index to the one square in the times table that took me the longest time to learn when I was learning my times table. 7 times 8. 56. The only way I learned this square in my times table is to remember 5, 6, 7, 8. Consecutive. I don't know. That was me. That was for whatever reason. All 100 squares of the times table, those were the two, 7 times 8 and 8 times 7, that I had the most trouble with. Okay, great. So now my fractions have common denominators, so I can add them by keeping the denominators and adding the numerators, for which 56 plus 7 gets me up to 63. And it would seem as though we're done. But for what fact? What can I do now? What do I need to do now that we didn't actually have to do in the last problem? Reduce. Right. There's an opportunity here to write this fraction in lower terms. How do we know that? How do we know that this fraction isn't actually already reduced all the way? They're both multiples of 9. Both the number 63 and the number 72 are multiples of 9. If we didn't see that, if I didn't spot that up front, of just factoring them out, 72 is 3 times, now let's just do it as 8 times 9, 63 is 7 times 9. And we could break the 9s apart further, but we really don't need to, because once we identify even a single factor which is common to both the numerator and the denominator, we can use that factor to reduce the fraction. All we have to do, what do we do with that 9 once we make that observation? Yeah, just divide both the numerator and the denominator by 9. And for the same reason that multiplying the numerator and denominator of a fraction by the same quantity remains the same fraction, dividing the numerator and denominator of a fraction by the same quantity gives you the same number. So 7/8 is the same number as 63 over 72. And sure enough, that was our answer for problem number 7. So looking back at the problem, where were the potential minefields in this problem? If you're going to screw up problem 7, where are you probably going to screw it up, do you think? Personally, I think the trickiest part of this process is probably the same as with a lot of fraction problems. Just, it's kind of a long slog because you have to do these 3 different operations. And by the time people have exhausted their brain power getting to here, sometimes, again, people will forget common denominators when they go to add, right? And in that case, they could get something like 14 over 81, and then you're like, all right, I'm done. But just, keep your wits about you, even on the longer fraction problems. Remember, anytime you add or subtract, even if you've already driven 1,000 miles in that problem to get there, you still have 500 miles or so left to go. Get that common denominator and forge forward.